Hello, welcome to the SETI Colloquium seminar series. Today we are fortunate to have Scott Gaudi from Ohio State University as a speaker. Scott did his undergrad at Michigan State University. Then he was a grad student at Ohio State, did postdocs at the Institute for Advanced Study in Princeton and Harvard-Smithsonian Center for Astrophysics. Scott is known among astronomers more than anybody else for the microlensing technique for finding exoplanets. And today, he'll be telling us about completing the synthesis of exoplanetary systems with microlensing. Let's welcome Scott.
So the standard lore goes that before 1995, this was the one planetary system we knew of around a normal star. That lore turns out to be wrong. For reasons which, if you're interested in, I can tell you about during the question session. But nevertheless, that's the lore, so let's stick with it. I've done a little revisionist history here and removed Pluto, as you can see. And if I tasked you to create your own planetary system, this might not be what you would come up with. Planetary system is a little unusual. The most massive planet is sitting right in the middle of the solar system. Interior to that are four big glorified balls of rock, and then as you go exterior to Jupiter, the planet masses more or less monotonically decrease in size and become ever further away from the sun. So this is a somewhat unusual architecture. Like I said, if I tasked you to create your own planetary system, you might be very communist about it and have them all be exactly the same size and exactly the same shape, or maybe just very orderly and have the most massive thing closest to the sun and then monotonically decrease in size as you go further away, but that's not what our solar system looks like. So one of the main goals of my field is, and really one of the main goals of trying to understand the solar system, we had 150 years to think about the formation of the solar system between the discovery of Neptune and the discovery, roughly 150 years, and the discovery of the first planets around other stars. And so, given enough time to think about things, you're going to come up with a theory. But if you think about what's required in order to understand planet formation, we think planet formation is a bottom-up scenario where you start off with the smallest dust grains that are about a micron sized, and then you grow up to the size of planets. That means you have to go up through about 13 or 14 orders of magnitude in size and 38 or 41 orders of magnitude in mass. Whenever you cross so many orders of magnitude in size or mass, the physics that governs the bodies that you're dealing with changes dramatically. And that's the challenge that we face in trying to understand planet formation. But like I said, it's hard. Like I said, given 150 years to think about it, we came up with a very good fairy tale to explain why our solar system looks the way it does. And I'm not going to do this fairy tale justice in any way, shape, or form. There are people in this room that have spent much more time in their lives trying to understand planet formation. But let me just try to sketch it out to you in very, very rough detail. The basic idea is that planet formation is basically the planets are the leftover dregs of star formation. Stars, we think, form in molecular clouds, dense clouds of mostly hydrogen and helium with trace amounts of heavier elements. About a 10 to the 6 solar masses in size. And then due to some random perturbation, some subset of this cloud begins to collapse under its own weight. The low angular momentum material falls to the center. The higher angular momentum material must preserve that angular momentum. It collapses to form a disk. This disk is initially hot, but over time begins to cool down. As it cools down, particulates begin to condense out of the gas in the disk, and exactly what particulates can condense out as the disk cools depends on exactly how far away you are from the parent star. So if you're very close to the parent star, basically the disk is very hot. It remains very hot, and so it's too hot to have solid material at all. Eventually, you cross a region where it becomes cool enough that you can condense out things like iron. As you get further out, you can condense out things like silicon and magnesium, which combines with oxygen to form rock, the bulk of the material that's in terrestrial rocky-like planets. And then somewhere around what we think is around 2.7 times the distance of the Earth from the sun, or 2.7 astronomical units, it becomes cold enough, about 150 degrees in the midplane of the disk, that you can actually begin to form solid water ice. And that's a very important location in the protoplanetary disk, perhaps the most important location in the protoplanetary disk, because the two most abundant elements in the universe that like to play well with each other are hydrogen and oxygen. And so the surface density of solid material jumps by a factor of several as you cross the snow line. And since we think we form planets in a bottom-up scenario from solid materials, that means that you have much more raw material to form planets. The other point is that the dynamical time, the time it takes to go around the star, and also generally the time scale that sets the time that sets the scale for when you can form things, is shortest just beyond this snow line. And as you get further from the snow line, your dynamical time increases, and therefore the time it takes to form objects increases. So as a result, we think we form the most massive planets quickest just beyond the snow line. And in particular, if we become an interior to the snow line, we don't have any ices, or what we also call volatiles, things that condense at low temperatures. And so basically you form small rocky cores with thin veneers of atmospheres, ultimately, which are probably created from internal processes. And then exterior to that, you form icy rock cores. Now, one important distinction is that for at least reasonable models of protoplanetary disks, you rapidly form masses outside the snow line. You rapidly get up to a mass of roughly 10 times the mass of the Earth via gravitational attraction. And you can see this plot here, which just shows the mass as a function of the mass of the Earth. The bottom line here is solid material. This dashed line here, dotted line here, is gaseous material. And then this is the total amount of mass. This is from a classic paper by Pollock et al. That describes the way we think giant planets form, called core accretion. So you rapidly run up to about 10 Earth masses of material of rock and ice. Then you run out of solid material. But you can slowly, hydrostatically, accrete gas. But once the mass of your gas envelope equals the mass of your solid envelope, then you can no longer maintain this hydrostatic equilibrium, and so you run away and rapidly accrete basically all the gas in your vicinity. And since you have much more gas than solids available, you can form planets of the mass of roughly that of Jupiter, or 320 times the mass of the Earth, or the mass of Saturn, 100 times roughly the mass of the Earth. So that's how we think giant planets formed. So you have the slow growth phase. And if you happen to cut off the gas disk by either accreting it onto the star or photoevaporating it during this phase, you'll get stuck. You'll get stuck at a mass of something like 20 times the mass of Jupiter. Sorry, 20 times the mass of the Earth. You'll be core dominated with maybe 10 or 20% of hydrogen and helium, and that sounds an awful lot like Uranus and Neptune. So you can think of Uranus and Neptune perhaps as failed Jupiters. Okay. In the inner part of the solar system, something very different happens. You run out of gas pretty quickly. Then you just have solid particles. Time scale for planet formation in the inner solar system is a factor of at least 10 times longer than that in the outer solar system. Your solid particles accrete. They form these things we call oligarchs that basically have most of the mass. Eventually, the mass of the oligarchs is greater than that of the mass of the leftover building blocks. And then they start to run into each other and eventually form planets like Mercury, Venus, Earth, and Mars. Now, there are lots of problems with this scenario that people have spent, again, their entire careers trying to understand, and I've glossed those over. I do not mean to belittle their work. It's a very hard problem. But that's the basic sketch that explains our solar system, and of course, it matches the data quite well. When you have one data point in 150 years to think about it, you better come up with a theory that matches your data pretty well. So we all know what happened next. The first companion was found around a solar-type star. That's the companion orbiting the otherwise unremarkable star 51 Pegasi, really otherwise sun-like star in the constellation of Pegasus. And this planet has a mass of roughly half the mass of Jupiter. But rather than being located in the outskirts of the planetary system, in particular beyond the snow line, where we thought at the time all giant planets must form, and really still think most giant planets must form, this planet was located only about 10 stellar radii from its parent star, well interior to the orbit of Mercury, and completely not predicted by this planet formation theory. In fact, the formation theory, this fairy tale I told you, would have told you that a planet like this could not exist. All right, so what did we learn from that? Well, then we learned that planet formation is really hard. In particular, we realized that there's a lot more physics that could, in principle, be going on. We now know that large-scale migration is very common in exoplanetary systems. We knew that there was small-scale migration in our solar system, but what I mean by large-scale migration is order unity changes in the orbital periods of the giant planets. So we now know that migration is important. Since we're looking at other stars, we have to think about the influence of the host star mass and the metallicity, the amount of heavy elements beyond hydrogen and helium in the star, and how that might affect planet formation. We have to understand dynamical interactions. Now that we know that planets can exist so close to their parent star, we have to think very hard about tides. Tides are one of those problems in astrophysics that are well known to be almost completely intractable, along with turbulence and magnetic fields. Disk properties are important. And of course, there are entire other models of planet formation that I have not even mentioned, which could well be, and there's evidence for them being viable, at least in some subset of planetary systems. And then there's lots of things that I haven't even mentioned. So meanwhile, what have we been doing in the last 20 years? Well, we've been finding a lot of planets. This is an extremely outdated plot. I apologize. It's kind of a pain to make these plots, but anyway, so I'm lazy and don't always update them. But this is an outdated plot that shows at least a subset of the planetary systems that we know of around other stars. I'll be showing plots like this a lot, so let me spend a little bit of time explaining it. Here on this axis, we're showing mass, spanning about 6 orders of magnitude in mass in units of the mass of the Earth. And here's semi-major axis spanning a little more than 4 orders of magnitude in semi-major axis. And keeping in mind this fairy tale that I've told you about how planet formation forms and how important the location of this snow line is, I've scaled to a model of the location of the snow line. So I can put planets orbiting stars around different masses on roughly the same plot without them looking too disparate. The points are planets that we know of, color-coded by their detection method. One of the exciting things about this field is that we now know of planets orbiting other stars detected with 4 or 5 different detection methods, depending on exactly how you count. The majority of the original planets were discovered by radial velocity here in red. Transits have quickly kept up. This is only a very small subset of the planets that have been detected with Kepler. These are mostly the ones with, that also have mass measurements. We know of many, many thousands more that have been detected by Kepler, but do not have mass measurements. I'll show you here. Maybe I'll show you here in a second. Okay, so what do we see? Well, okay, so we've detected thousands of worlds. Okay, so the observers have been busy in the last 20 years. The theorists, of course, have been busy as well. They quickly realized after 51 Peg was discovered well, we knew migration happened all along. In fact, there was a seminal paper that had been written long before 51 Peg that was discovered, arguing that giant planets should migrate in their disk. That paper just couldn't figure out which direction they should move. We now know that they should move inward generally, not outward, at least for some forms of planet migration. The theorists have advanced to the point now where they're able to make ab initio predictions using parameterized models of the physics of planet formation that can now populate these diagrams with what they think planetary systems should look like. Okay, this is a very, very old, this is one of the first versions of this plot. I show it just because it is one of the first ones to do this. I like it. But what you see is that there's a little hard to see in this, but there's three main populations of planets predicted by these theories. This is fairly generic to these kinds of theories. There's this population of these terrestrial planets, these rocky planets, similar to our own rocky planets. There are the population of these cold, sub-Neptune, Uranus mass planets. You can think of these as the failed Jupiters. And then there's the Jupiter-size mass planets, which have somehow managed to form here and migrate interior to the snow line, where they can be found with the methods that we've developed today. So, how do we test these theories? How do we better try to understand planet formation? Well, the basic idea is that we hope that the physics of planet formation is imprinted on the distribution of planet properties that we can then go and measure. And so by looking for features in this distribution, we can hope to look for smoking guns of the physics of planet formation. So for example, various predictions have been made for a planet desert, paucity of giant planets around low-mass stars. This is because low-mass stars have low-mass disks and longer dynamical times. So we think that in those cases, the planets get stuck in this long timescale phase of giant planet formation, and so never make it to this critical mass for core accretion, and so never develop this very thick envelope. These models generically predict a large population of free-floating planets, which in principle we can try to detect. So the plan is to measure these distribution functions, the number of planets as a function of whatever property you can tag them with, mass, radius, semi-major axis, orbital period, other things if possible. In other words, measure the demographics of exoplanets in the same way you go and take a census of people and try to figure out where they are and where they live and what their properties are. Measure them as accurately as possible over a broad range of properties, and then try to compare with your theories and see if you can look for these features predicted by these theories. Okay, so here's now I'm plotting both the planets we've observed and then the theoretical planets. And what do you notice? Well, it's quite striking. One thing you notice is that the majority of the planets in our solar system are completely disjoint from the planets that we know about orbiting other stars. The one exception to this is perhaps Jupiter and maybe Saturn, but the terrestrial planets in our solar system and Uranus and Neptune are not being probed by any of the methods that we have developed today. Okay, so the planets that we're discovering around other stars look very different than our own solar system. Now, Kepler, the other thing you notice is that the planets we've discovered are largely disjoint from these two large reservoirs of planets predicted by planet formation theory. They're also disjoint from the third large reservoir predicted by planet formation theory, that is, free-floating planets. Okay, so we're seeing a very biased subset of planetary systems, at least if you think our solar system is, at least there are other solar systems like ours are out there, and if you put any credence whatsoever into these planet formation theories. So Kepler has begun to fix this problem by digging into this reservoir of terrestrial planets, and indeed has found many, many, many such planets. But what about this out here? And that's where that's where the microlensing starts to come in. Okay? So Kepler has begun to take this planetary census, and what I'm going to argue to you is that the telescope called WFIRST, which is the successor to JWST, is going to complete the census of planetary systems and then give us this data set we need to understand planet formation. Okay? And WFIRST will also be able to tell us about free-floating planets. Okay, so that gets me to the technique that I spent the majority of my career on, 20 years now, called gravitational microlensing. Okay, so what is microlensing? Well, in principle, it's quite simple. Imagine staring at a source, a star, in the galaxy for long enough. For our purposes, we're going to be talking about stars in the center of our galaxy, the so-called galactic bulge. It's about 8 kiloparsecs, or I guess that turns into about 24 light year or 24,000 light years away, if I did my math right. If not, please correct me. But anyway, you stare at a star in the center of our galaxy for long enough, And eventually another star is going to pass very close, which we'll call the lens, will pass very close to your line of sight to that more distant star. So stars in the galaxy are moving in the potential well of the galaxy, so eventually they will occasionally pass by very close to each other. And what I mean by very close is about a milli-arc second. Okay? And remember, our eye can resolve about one arc minute in size. So this is a very small angle indeed. Okay? When that happens, light from the source star that you were staring at, which would have been going in this direction, gets bent by the gravity of this foreground lens into your line of sight. And so rather than seeing the source here where it really is, you see it displaced by a certain amount due to the gravity of the lens. Now, in fact, what happens, now imagine if the source and lens are perfectly aligned. Okay? This does happen occasionally, but it's rare. Then the source, so now we're looking at it from our perspective, okay, so that was a side view. This is now from our perspective. So this red dot is the source that we've been staring at. And in fact, you'd have to stare at one star to get a microlensing event for about 100,000 years if you were going to wait for this to happen. And then this black dot here is the lens. That lens will image the source into a ring, which we call the Einstein ring, which has a radius, not surprisingly, equal to the angular Einstein ring radius, which is about 7,000 micro-arc seconds or 0.7 milli-arc seconds in size for a typical mass of our lens. That is far too small for us to be resolved. In the more usual case where you have slightly imperfect alignment, you get two images, one outside the Einstein ring, one inside the Einstein ring. The separation of those two images is about twice the Einstein ring radius. So again, about a milli-arc second, and again, far too small to be resolved. Although I do find it quite amusing to think that there are all of these double stars out there waiting for us to see once we get technology good enough to resolve these kinds of angles. So we don't see this, however. But what we do see is that if you look carefully, the area of these two images in blue is, and count this up and do this by eye, is larger than the area of that source, okay, the original unlensed source. And since surface brightness is conserved always, that means that the magnification of this lensed source is larger than it would be in the absence of this lens. So we can measure this magnification, and that is the signature of a microlensing event. And since the source and the lens, and us for that matter, are all moving in the potential well of the galaxy, this alignment is not a fixed function of time. The magnification depends on how closely aligned you are. The closer the alignment, the higher the magnification. But as you get closer to the lens or further away, your magnification will increase or decrease. And so what you get is this animation here. In this case, I'm fixing the lens in the center. It doesn't matter. It's the same thing. I'm moving the source behind it. But as the source approaches the lens and then gets further away, you can see the two images trace out these paths. And then if you look here on the bottom, you can see the background star get brighter and then fainter again. And that's the signature of a microlensing event. Einstein is the first person to predict that this would happen, although he famously predicted because of this alignment had to be so precise that it would never be observed. It has now been observed many thousands of times, probably close to 10,000 times. Of course, the trick is not to look at one star for 100,000 years. The trick is to look at 100 million stars, and then you can get a lot of microlensing events. And the reason why we look in the center of our galaxy is that there are 100 million stars per square degree, roughly, in our galaxy, in the center of our galaxy. Now, the time scale for this microlensing event is about 30 days, although it can vary from 1 day to hundreds of days. And the problem, of course, is that you don't know when this is going to happen. So you have to look at all 100 million, or maybe if you're being lazy, 10 million stars in the galactic bulge just to get a few microlensing events. And you don't know when they're going to happen, so you have to monitor them continuously on timescales of a few days if you're going to see these microlensing events. The other problem is that the only thing you really measure from this microlensing event is its time scale, and that depends both on the mass and distance to the lens, and its velocity relative to the source, which you do not know a priori. So it's difficult to learn a lot about the mass of the lens from this. I'll tell you a little bit more about that later. All right, so what does this have to do with detecting planets? Well, let's say this foreground lens, again, not the star that you're looking at in the center of the galaxy. That star, for all intents and purposes, is a flashlight. That's all you care about it. Where we care about the lens that's actually in the foreground, that's whose gravity is actually doing the brightening. Let's say that foreground lens happens to have a planet. Here I'm showing that planet in purple right here. And that planet happens to be located near the path of one of these two images. Well, as that image sweeps by the planet, the gravity of the planet is going to cause the light rays to bend in the same way that its host star did. And it's going to give you a little extra brightening on top of your otherwise normal microlensing event, which you can see right there. Okay? The time scale for this little brightening is short. It goes as roughly the square root of the mass ratio, which I'm calling here Q, between the planet and its host star. So if you run that out for a Jupiter-sized planet, square root of roughly 1,000th times 20 days, you get about a day. So the time scale for this deviation is very brief. It's also unpredictable. You don't know when it's going to happen. So you have to monitor these microlensing events on time scales of days. If you wanted to detect a Jupiter-mass planet, if you want to detect an Earth-mass planet, you have to do it on the time scale of hours. Okay, so you have to monitor, detecting planets with microlensing basically amounts to monitoring roughly 100 million stars continuously every hour for at least several months if you want to detect a planet. Okay, so this is not an easy thing to do. Now, one thing you can notice is that the planet, the detection sensitivity, your planet has to be close to one of these two images to get a significant perturbation. If you can see that when the primary event is magnified here, roughly between -1 and 1, the images are always close to the Einstein ring. So that means that you're most sensitive to planets that are close to the Einstein ring. All right? And that turns out to be about 2.8 AU for a half solar mass lens. It's about 5 AU for a solar mass lens. So that turns out to be roughly twice the location of the snow line for typical models of a snow line. Okay? So microlensing is most sensitive to planets that are about twice the snow line from their parent star. And so that means it's very complementary to other methods which are sensitive to planets much closer in. And I'll show you that here in a second. So if you're interested in finding planets like Jupiter or Saturn, which we think form beyond the snow line, this is the way you're going to do it. Now, one interesting point is that microlensing is directly sensitive to planet mass. It works primarily by perturbing images. You don't require light from the lens or the planet itself. So that means you can detect planets from basically our local neighborhood to the center of our galaxy. You can determine the galactic distribution of planets. In fact, you don't even need a host star at all because the planet has gravity itself. So you can detect wide or even free-floating planets if possible. The only planets you're not sensitive to are those that are perturbing these very small images, and that's because they're highly demagnified. Okay? All right. I mentioned free-floating planets. Again, you don't require the host star at all because the planet has gravity as well. So this is a simulation of what a free-floating Mars mass planet detection might look like. And so you can detect free-floating planets in this way as well. And again, like I mentioned, that's a generic prediction of planet formation theories.
I see a new word, solivagant.
A solivagant. It's actually not a new word. If you go and you look it up in the dictionary, it means I can't remember exactly, but it's basically wandering, free-floating world. Okay. The last thing I want to mention is that there is a lower limit to the mass of the planet you can detect. This lower limit is set by when the angular size of the planet depends on the angular size of the source is equal to the Einstein ring of the planet, because then you're only magnifying a very small portion of the source star. And that mass turns out roughly to be about, I guess I want this one here. That mass turns out to be roughly about a few times the mass of the moon. Okay, so the smaller your planet gets, the longer, the more washed out your signal gets. But you can detect planets down to a few times the mass of the moon with the right experiment. Okay, and that's significantly below the mass limit of essentially any technique except for pulsar timing. Let me just skip that. Okay, so drink the Kool-Aid. You're sensitive to planets beyond the snow line, roughly twice the snow line for typical parameters. You're sensitive to planets that have very low mass, roughly 10% the mass of Mars, or roughly the mass of the moon. You can detect very long period and free-floating planets from about a half the distance of the Earth from the Sun out to infinity. You're sensitive to planets orbiting stars with a wide range of host masses and throughout the galaxy from here to the center of our galaxy. Okay, so it has a lot of advantages to it. Now, not everyone is always immediately sold. So this is one of my favorite quotes from Deborah Fisher. I don't understand. You're looking for planets you can't see around stars you can't see. Fair point. Microlensing is a cult. Also a fair point. Okay. Nevertheless, so I briefly just want to what time we got? I think I'm going to skip this actually. Just the point being that actually measuring the mass of the lens itself and the planet itself requires a little bit more work because of this degeneracy that I mentioned to you before. Right now it is not routine. We can do it for a subset of events, but in the future it will be routine. So rather than raise an alarm, which won't really be an issue between 5 years from now, I will just skip this. All right, so this all sounds totally made up. I can understand that, but it really does happen. And so here's an example of actual data from the first planet discovered by gravitational microlensing. In the bottom, we see a model. And the model, you can see a little red dot tracing out the brightness as a function of time. And in the top is an actual image from the center of our galaxy from the Ogle collaboration. You can see a bunch of stars that are being really, really boring and do absolutely nothing. And then you can also see a star. Conveniently, we were able to find it because it had a green circle around it. And you can see that that star itself is getting brighter and then fainter and then brighter. And you can see the little blips that are caused by those sharp spikes. Those sharp spikes are the indication of the planet orbiting this host star. Okay, and then the rest of the light curve is just due to the host star itself. Okay, so this was the first planet discovered by microlensing, roughly a Jupiter mass planet. All right, so enough about the intro, yeah.
So that was only one planet, even though there were two blips?
Yeah, and for reasons which are not worth going into right now. But I can try to explain it to you afterwards. Microlensing turns out to be a little bit more complicated than other planet detection methods in terms of the phenomenology of the light curves that you see. It has to do with the fact that you have some interesting optics when you have a microlensing event. You can think of it as an astigmatism that gives you these sharp features. So if you ever look at a glass of water, and sometimes you see these funny refraction kind of features, it's basically the same thing. Okay, so all right, enough about intro. What about results? Okay, so we found, I don't know, a couple dozen planets by now with microlensing, and we're not nearly as many as radial velocity or transits. But as I argued, we're probing an entirely new region of parameter space. So we've learned a lot about planet formation, even though we haven't detected a lot of planets. The first result to come out of microlensing was that we've discovered a population of very cold, low-mass planets. So this is the first such discovery. You can see this beautiful microlensing light curve, which for almost the entire part of it looks completely normal. But then if you see this little zoom in there, right there, you see a little extra little bump. That little bump is due to a planet of roughly 5 times the mass of the Earth. Okay? And we found many such systems like this, and we know that they're actually quite common, and in particular, much more common than their giant Jupiter mass brethren. Okay, so failed Jupiters are much more common than Jupiters themselves. Perhaps not a surprise, but anyway, there's the result. Here's an interesting system. In this case, again, you look at the bottom, the second from the bottom panel, it looks all the world like a normal bell-shaped microlensing event, which you've now seen about 6 or 7 times in this talk. But you can also see there's a little feature there. In this case, it's a dip, not a bump. And if someone wants to ask me afterwards why you get a dip and not a bump, it's one of the most common questions I get. But it also has to do with the nature of the optics of the gravitational lens itself. But in this case, what's going on is you're taking light away, light that the host star would have been bending into your line of sight, and the planet is saying nope and pushing it back out of your line of sight. And so you get this beautiful little dip. These dips had been predicted for, 15 years. So in my thesis, there's lots of little imaginary dips made from models. And so the first time we saw one of these, for me, was quite amazing. And you can see the model goes through the data like beads on a string. It's quite impressive. But in this case, we were able to actually, this degeneracy that I mentioned was broken. We were able to measure the mass of the planet. And the planet turns out to be about 10 Earth masses. And that number should be familiar to you, because when I went and told you about this original model for core accretion of giant planets, the Pollock et al. Model, the 10 Earth masses is the mass that you get stuck in, roughly, if you don't reach this critical core mass and accrete this giant envelope. So in this case, and the host star itself is a low mass star, so this is exactly following this fairy tale where around low mass stars, it takes so long for you to get to this critical mass where you can accrete this massive gaseous envelope that your disk has gone away, and so you get stuck at roughly 10 Earth masses and you're a failed Jupiter. Okay? Now, whether or not this is actually something that we see generically, where it's going to require many more detections like this, but it is a subtle hint that we're seeing this process in action. And I should also mention, so here's what I was showing you before. There's a point here. So what I was showing you before, this is this place where if you run out of gas in your disk here, you'll get stuck at roughly 10 Earth masses. I should also say there is evidence for this in the Kepler data as well, this feature at roughly 10 Earth masses. Although, of course, in the case of Kepler, we're talking about separate periods that are much shorter, a few hundred days, whereas in this case, we're talking about periods of several years. So it's a very different regime of the planetary system. Okay, so those of you who have ever seen me give a talk have seen this an ad nauseum number of times. It is my favorite light curve. It is showing brightness in astronomical units. So, you know, we're backwards, so smaller numbers are brighter. So brightness increasing as you go up, and time as you go to the right. In this case, things are a lot more complicated, as you can see. You can see an overall thing that looks something like the bell-shaped curve, but there's a lot more going on, which are conveniently labeled by 1, 2, 3, 4, 5, these other features. Somewhere around 1, we thought something weird was going on with this data. We kept watching as the data came in. We kind of missed 2, actually. We didn't notice this feature until after the event was almost over. But then as 3 came in, we knew something weird was going on. I was actually a postdoc at Harvard. I was modeling this event. I was coming, you can barely see this gray line going through the data. I was coming up with these models, trying to predict what this data would look like. And right around when the data 3 came in, I came up with a model that predicted that there was a Saturn mass planet around this object. This was around 1 o'clock in the morning, as all postdocs work until 1 o'clock in the morning. So I was super excited. I sent an email to all my collaborators. You can see them all listed here. Microlensing, because it's an unpredictable phenomenon, we require around-the-clock coverage. So we have collaborators in New Zealand, in Chile, in South Africa, in Perth, in Eastern Australia, all over the place. So we can get continuous coverage, weather permitting. So 3 o'clock. So this 3 feature happened. I came up with this model. I sent an email to all my collaborators all over the world. I predicted where the next night's observation should be so that people could plan what they were doing, plan their exposure times, etc. I predicted that it should be down here, roughly where the end of my arrow is. And so then I went to bed and I slept about like 4 hours because I was super excited. I couldn't wait to see the new data come in. The new data came in, and rather than being right there, it was all the way up here. Completely wrong. Well, I mean, my model was completely wrong. The data were what they were. So I was kind of super depressed, and you know, I was kind of like wondering about my efficacy as an astronomer. Meanwhile, the data kept doing what it did, and it went down here, and then it created this bump here, which is exactly actually what I had predicted when I had sent off the email. It did, the rest of the light curve did exactly what I predicted. So I pounded my head against the wall for a long time trying to understand this feature 4, which just didn't fit my model at all. And then I kind of had an epiphany, and I realized, wait, maybe it's not that there's one planet here, maybe it's that there's 2. And indeed, if you put another planet in the system, you can fit feature number 4 perfectly. So this is a multi-planet system, the first such found by microlensing. The interesting thing about this system is, again, we can measure, in this case, we break the degeneracy, we measure the mass. The host star mass is about half the mass of the sun. The first planet that I had found was roughly the mass of Saturn, located about half the distance of Saturn from the sun. And then the other planet is roughly the mass of Jupiter, about 3/4 the mass of Jupiter, located roughly half the distance of Jupiter from the sun. So it's as if you took the Jupiter-Saturn-Sun system and scaled it down by a factor of 2, which is exactly what you would predict based on this fairy tale and the location of the snow line around a star around half the mass of the sun. So this system at least, or at least the Jupiter-Saturn analogs in this system seem to have formed, or could plausibly have formed, in the same manner as our own Jupiter and Saturn. So we built it as a Jupiter-Saturn analog, you know, got in the New York Times. That was my 15 minutes of fame. Okay, I'll skip that. One thing is that we can actually use this detection and then a bunch of other planets that we've detected to try to estimate the frequency of solar system analogs, or really Jupiter-Saturn analogs, and you come up with roughly 15%. Now with one detection, there's a large error bar associated with that, but it does mean that Jupiter-Saturn systems are neither the majority of planetary systems, most likely, nor are they exceptionally rare. Okay. Let's see, what do I want to say about this? Let's see. The other thing you can do is you can actually try to estimate the frequency of planetary systems using a bunch of different methods. Here I'm showing the frequency that we inferred from our survey here in red. This is for planets from roughly a few times the mass of Jupiter down to about 10 times the mass of the Earth. We find that such planets centered around the mass of Saturn are exceptionally common. Most of our host stars are low mass, roughly half the mass of the sun. So these are typically M dwarfs. And if you do a little bit more work with other data, you can find that the mass function of planets from microlensing is extremely sharply declining, such that low mass planets are much more common than high mass planets. Now you can compare the frequency of planets we find to the frequency of planets found by radial velocity orbiting similar stars, M dwarfs, and you find that they are different by over an order of magnitude. Those are these points shown here for the HARP survey and then the CPS survey of Johnson et al. They're different by an order of magnitude. And this is perhaps a puzzle because, as I said, this model of planet formation predicted that giant planets should be very rare around low-mass stars, just like the radial velocity surveys found. And of course, this was hailed as a victory for the core accretion model. But we actually find that giant planets, albeit those slightly less massive than what they're looking at, are exceptionally common, almost as common as super-Earths around solar-type stars, which we all know are very common. So what does this mean? Well, the mass function is very steep. And so my graduate student, Christian Clanton, went to try to predict whether or not he could try to understand in the region of overlap between the microlensing surveys here in purple and the radial velocity surveys in green if in the region of overlap these two surveys were consistent. And so what he did was he used the frequency of planets inferred by microlensing to predict the number of planets that radial velocity surveys should see. I won't go into the details of how he did that, but the basic result is he predicted that they should see roughly 5 planets with a relatively large error bar, and what they actually see is 4, well within 1 sigma, indicating that these surveys are completely consistent. So then the next thing he did was went about, I'll skip that, to try to compare, to try to combine the results of these two surveys. And so now what I'm showing is what's sort of become known as the Howard plot. So each one of these boxes shows the frequency of planets in a region of parameter space, covering 5 orders of magnitude in the period, and then 4 orders of magnitude in the mass. The darker the color, the more frequent the planet. And what you see is that giant planets around M dwarfs are relatively rare, but low mass common planets are extremely common. Particularly, there's 2 reservoirs of low mass planets around low mass stars here that were discovered by radial velocity, and here that were discovered by microlensing. If you compare this with Kepler results, Kepler covers just this range of parameter space. So we're covering a much broader range of parameter space than is discovered by Kepler. Okay, so you can start just adding things up if you like. Let's think about giant planets, planets that are above that critical mass of core accretion. We find that there's about roughly 20% of M dwarfs have a giant planet with a substantial error bar. Okay, so giant planets are not rare around low mass stars. They are less common around low mass stars than they are around high mass stars like the sun, but they are not rare. You can also just add up everything, and you come up with 2. So every M dwarf on average has 2 planets, again with the substantial error bar, which will decrease over time. Okay, so planets are extraordinarily ubiquitous in the galaxy. And since M dwarfs are actually the majority of stars in the galaxy, 70%, that means that planets are very, very common in the galaxy, more common than stars. Microlensing has also discovered a population of free-floating planets. I won't have time to go into this in too much detail, but basically we find an excess of very short timescale events that cannot be explained by stars or brown dwarfs, and that excess implies that there's roughly 2 free-floating Jupiter mass planets per star. Where these came from, no one knows, but that's what we're finding. Okay. So I'll spend the rest of my time now talking about what we can hope to learn from microlensing in the future. The first thing that's going to happen is what's called the Korean Microlensing Telescope Network. As you can imagine, this is funded by Korea. This is 3 1.6 meter telescopes, one located in SAO, one in Siding Springs, and one in Chile. As I said, I reminded you need continuous coverage, so you want telescopes located at a range of longitudes, and of course the galactic bulge is visible from the southern hemisphere, so you have to go to the southern hemisphere. Each one of these telescopes is equipped with a 4 square degree field of view, which means you can cover almost the entire galactic bulge in only 4 pointings. And that means you can get extremely high cadence and be sensitive to Earth mass planets in principle. The plot on the right shows a somewhat more updated version of the planets that we know of, created by my ex-graduate student, Kalen Henderson, who's now moved on to JPL as a postdoc. He did simulations of this survey. This green line shows the region where we'd expect 10 planets, above which we could expect 10 detections of planets per year, and then this dotted line is where we could expect the detections of 1 planet per year. And then this dash line here is everything above this. We would expect 1 free-floating planet detection per year if every star had a planet of the given mass. Okay, so the next generation microlensing surveys will reach down at least an order of magnitude in mass, and will tell us about free-floating planets with mass down to roughly the mass of the Earth. Okay, these 3 telescopes have been built, the cameras have been assembled, data is being taken. I'm going to show you now the first planet discovered by this survey. This is just showing data from 2 observatories. The third one was being commissioned when this planet was discovered. You can see again this well-known now bell-shaped curve, but this little divot is due to the planet. Here's a blow-up of it. In this case, it's a pretty unremarkable Jupiter mass planet, but it does show that this survey is now fully operational, and so we can hope to be looking for lower mass planets and much more interesting discoveries soon. Okay, so how do we get below a mass of the Earth? I promised you that you could do this, but you can't do this from the ground. So you need to basically monitor hundreds of millions of bulge stars continuously on a time scale of 10 minutes. You need about 1% photometry in order to get the detections, because your deviations are a few tens of percent. So these deviations are not small, right? So if you've heard talks from Kepler, people are talking about getting 10 micromagnitude, right, or 10 to the minus fifth, or 10 to the minus 3% photometry, because they're trying to detect things that are 1 part in 10,000. We're trying to detect things that are 1 part in 100. So these deviations are much, much larger than what Kepler requires, which is good because our stars are a lot fainter. Now we have to actually look at main sequence stars in the galactic bulge in order to detect the smallest planets, because those are the smallest stars in the sky, and the smaller the star, the smaller the planet you can detect. We need high resolution for technical details I won't go into. All of this basically tells you that you have to go to space. And you can see why in this figure on the right. These 2 pictures are exactly the same field of stars. The one on the right is seen from HST. The one on the left is what you see from the ground. Okay, so having high resolution really helps you a lot. Things that look like single stars from the ground, you can see are actually multiple collections of stars. Okay, and that makes your life a whole lot harder. But if you can do this from the space, then you can resolve out all of the stars and you can do much better. It also allows you to go to redder wavelengths, where the atmosphere is not so much in the way and the dust is not so much in the way. That gives you smaller sources, more extincted fields, gives you a higher event rate. Space gives you better resolution. And of course, in space, you don't have to worry about the sun coming up, so you can look you can look continuously, and you don't have to worry about getting this longitudinal coverage. It also allows you to get smaller systematics for reasons I won't go into. So the bottom line is that if you can go to space, then you can get planets with mass less than that of the Earth. You may even be able to detect planets in the habitable zones of their parent stars. You can get free-floating Earth mass planets and even down to Mars mass planets. And you'll get mass measurements for all of your planets. Okay? So that brings you to WFIRST. What is WFIRST? Probably some of you have heard of this, but anyway, it's the Wide Field Infrared Survey Telescope. It is a telescope that was constructed by the last decadal survey from bits and pieces of other proposals, little Frankenstein kind of thing. It was the #1 recommendation of the last decadal survey for a large space mission. Basically, the idea was to do 3 different sets of science. One was a survey of the galactic plane. One was to do dark energy through baryon acoustic oscillations, supernova, and weak lensing. And then the third was to do a microlensing survey, as I've just described. So these 3 were the 3 equal science areas. So back in 2010, they assembled a team to try to figure out whether or not this Frankenstein could really be realized. So I was part of that team from the very beginning. We came up with a couple what's called design reference missions. So these are basically notional missions that have been flushed out in some detail to see if this dream of the decadal survey could be realized. The answer turned out to be yes. But then something very interesting happened. Then what happened was NASA discovered in the warehouse somewhere, actually in Excelis lab in Rochester, 2 telescopes that had been donated to them by the National Reconnaissance Office. So that they had 2 extra telescopes they didn't need anymore. 2.4 meter telescopes. We aren't supposed to know what these telescopes were for. We all know what these telescopes were for. We were told that we could do anything we wanted with these. NASA was told they could do anything they wanted with these telescopes except point them back at the Earth. But we are not supposed to know what these telescopes were for. And so they were basically 2.4 meter telescopes, very much like Hubble, except a little faster, which allowed them to do wider field. And so they could do this wide field instrument. It basically consists of mirrors and spacecraft assemblies. And so we decided then, so one of these was decided to be studied to see if it could do WFIRST. The answer is yes. And we also considered now a coronagraph so that you could do direct imaging of exoplanets as well. So this was added on. These are the properties. I'll just leave this up here for your reference. It's basically Hubble with 500 times the field of view. That's what you should think of it, and infrared detectors. Okay? And a coronagraph that allows you to do direct imaging of Jupiter-like planets. Not Earth-like planets, most likely, but Jupiter-like planets. And so it enables all of the science that the original WFIRST imagined, plus direct imaging of planets itself, so it's very, very, very exciting. So we just submitted our final report, a year ago now. You're welcome to download it. It's exceptionally long, but you can maybe just read the summary. It's quite exciting. Okay, so in terms of microlensing, my postdoc Matthew Penny did a bunch of simulations. Basically involves coming up with a star field, injecting microlensing events, and seeing which you recover. This is an example of a microlensing event due to a planet with the mass of Ganymede. That deviation there is due to a planet of the mass of Ganymede. Okay? All right, and then the thing on the right is the deviation due to a free-floating planet with the mass of Mars. Okay, so just to give you a sense, compared to Kepler, we're all very familiar with Kepler. Just to remind you, if every single solar system looked like ours, Kepler would have found 0 planets to date. 0. Okay? Now, we know it's found 4,000 planets, which means that a lot of planetary systems look absolutely nothing like ours, but it also means that it's not telling us anything about planetary systems like ours. If you look at the Kepler search space, this is a plan view of our solar system. I've put Pluto back in now because it helps my case. But you can see that the blue dot here in the very center is where Kepler is sensitive to, and the red is where WFIRST is sensitive to. Now, this plot's a little unfair because planet formation is almost certainly more logarithmic than linear. So if you put it on a logarithmic plot, it looks more like this. Same sort of plot I've been showing you. Planet mass on this axis, planet separation, semi-major axis in AU. So there's the Earth, there's Venus, there's Mercury, there's Mars, Jupiter, Saturn, Uranus, and Neptune. Okay? So with Kepler plus WFIRST is sensitive to everything with mass greater than the Earth from 0 to infinity, because it's sensitive to, WFIRST is sensitive to free-floating planets with mass of the Earth. So this will give us together the most complete census of planetary systems available. You might be wondering what these things are here. Anyone want to guess what that is? Yeah. That's the moon. That's Ganymede. That's Titan. Okay? All right. Okay. And the number of planets we hope to detect is not quite as large as Kepler, but it's roughly 3,000. All right? So that means we're going to get very good statistics, and we're going to be able to probe unusual systems that you wouldn't find. So this, to me, is one of the most exciting things about WFIRST, is that whenever you open up a new region of parameter space with a large number of detections, you can always expect to find, if we've learned anything in this field, it's that Mother Nature is way more imaginative than we are. You can expect to find a lot of things you didn't expect. Oh, the blue points here are, by the way, simulated detections that you'd get with WFIRST, so don't pay no attention to those. They're almost certainly wrong. All right, there's some sensitivity to habitable zone planets. In the same way that Kepler is basically going to be lucky if they find any Earth-like planets in the habitable zone, WFIRST will be lucky if it finds any Earth-like planets in the habitable zone. But the nice thing is that we're coming at it from both sides, and so that means that we can do a pretty good job of interpolating the two missions and getting a robust estimate of the frequency of Earth-like planets, which is important for future direct imaging missions. I'll skip through this, and then I'll just end with my summary. Thanks.
All right, questions. Let's start from that end.
Russ.
Hi, Scott. So, is this thing on?
Yep, I can hear
you. Your plot of planet frequency versus semi-major axis seems, I mean, the error bars are large, but it seems to be roughly consistent with Bode's law, where you have roughly constant occurrence rate versus log semi-major axis. Does that continue all the way out to where planets are unbound, and does that connect in fact with free-floating planets in a way you would expect if Bode's law continued all the way out there?
I don't think
or does it stop somewhere?
All right, yeah. So question is, does the planet frequency seems to be consistent with Bode's law, which is roughly equal numbers of planets per log semi-major axis or period. Does it continue out to free-floating planets? The answer is we don't know. My graduate student, Christian Clinton, recently finished a paper showing that it is consistent with planets out here and maybe a little bit further, but that's as far as we know. I would be surprised if there isn't a break somewhere between bound planets and free-floating planets. This is 10 to the 5 days period. So in this plot, you should not believe this last column because it's a lower limit. But like I said, my recent work by Christian Clanton shows that indeed it does continue out more or less consistent with uniform and log semi-major axis throughout this column here as well.
So in a number of your slides, including the one you've got up right now, you talk about the orbital period of planets that you've detected with microlensing. And of course, microlensing only gives you a snapshot. It can give you the distance between the host and the planet at a particular moment in time. And I wonder if you could say a little bit about the statistical work that I think you do. First, to argue that the planet and the host are not just coincidentally passing by each other, and secondly, to tell us something about what the actual size of the orbit is likely to be.
Yeah, so let me answer the first question, which is how do we know that the planet and the star are not just coincidentally by each other? Basically, it's because the probability of getting any single microlensing event is about 1 in a million. And so the probability of having two around the same star at the same time is 1 in a trillion. So I don't know. I'm a pretty conservative guy, and that basically tells me that it's almost certainly bound. The second question is, you're right. It's sensitive to technically microlensing is sensitive to the projected separation at the time of the event in units of the Einstein ring radius. So we have to go through a lot of marginalization and rigmarole to convert this into what radial velocity will see. So what we do is we take the planet population inferred by microlensing in microlensing observable space. We marginalize over things like the orbital eccentricity and the inclination and the angular Einstein ring radius, and then we project that using the inclination distribution, because radial velocity is sensitive to m psi and I, onto the observable space in radial velocity, which is what you see here, and that's what those contours are. And then what we do is we put detection efficiency curves for radial velocity and ask how many they should detect. So that is the bulk of the work, but it is the least interesting thing, which is why I spent absolutely no time on it. But yes, we do all of that horrible, ugly thing in order to map the unobservable to an observable and do a fair comparison. That's right.
Hi.
Yeah.
So since we are at the SETI Institute,
Yeah.
If you get this WFIRST off the ground,
Yeah.
since it does go into the infrared,
Yeah.
I'm wondering if you would be able, in theory, to differentiate between a free-floating planet and, say, a Dyson sphere, or that's no moon, it's a space station.
So I don't actually know off the top of my head the internal flux, the flux of a Dyson sphere, but I'm guessing that it's going to be far below our detection threshold. So I think the answer is probably not, unfortunately. Now, yeah, probably not.
Has anyone ever detected a planet with microlensing and another technique and had the results agree with each other?
That's an excellent question. Okay, so how do you know we're not? How can you prove to me that we're not just making all of this up? Okay, or has any of these results been confirmed? Not for a planet, but there was a binary lens, microlens, where we were able to actually map out all of the orbital elements because we were able to detect the orbital motion of the binary over the course of the microlensing event. That gave us a prediction for the semi-amplitude and the period of the binary, and the host star happened to be bright enough that we could go get radial velocity measurements, Doppler measurements, to confirm that orbital solution, which was indeed confirmed.
So I'm just wondering, what makes you think there's not a solar flare or a tiny black hole or something that causes these blips?
Yeah, so what makes us think that these things are not that is because that, right? Stars don't do that. There's no stellar phenomena that we know of that looks anything like that. And that model, which is, comes from a fifth order complex polynomial that you have to solve in order to come up with this exact precise shape, matches the data so perfectly that there's basically no astrophysical false positives that we have found or seen anything close to mimic that signal. That's one of the nice things about microlensing, is that there's essentially no false positives that we found. Now, for extremely poorly covered perturbations, right, then there may be some ambiguities. And in fact, there was one case where we found something that was it's called an RSCVN variable star, which happened to look like a microlensing event, sort of, but we were able to get enough extraneous data to demonstrate that it didn't actually behave like a microlensing event would. But by and large, to 0th order, you can just assume there's essentially no false positives in terms of the variability that we see. Solar type stars vary at millimagnitudes. We're looking for deviations, you can see here, at 20%. Solar type stars do not vary at 20% unless they're extremely young and extremely active, which those stars are extremely rare. So,
I've got a question about the snow line.
yeah.
Isn't it the case that water vapor, gaseous water, will condense to solid water as a function of the partial pressure of water in the environment? And
Yep.
wouldn't that be arbitrary depending upon the star? And wouldn't you have to know the partial pressure of water around any given star to know where the snow line is?
Well, I think for most protoplanetary disks, they're essentially pure vacuum. So what you care about is the condensation temperature in a vacuum.
That's a function of the partial pressure of water in the environment.
Oh, yeah, so I agree. So I see what you're saying, yes. So, yes, the models of the snow line themselves are extremely uncertain, I would say. So I mean, the models that I've used, I wouldn't trust them. They're basically illustrative. Absolutely, right? So so in our solar system, it's this incredible catch-22, right? The place where you actually can have water, right, is beyond the place where you can have liquid water on the surface of a planet. So that means that probably the water had to come from someplace else, right? And so it's completely this catch-22. Now, that might not be true of other systems. There are some models of snow lines that predict that the snow line can be all the way interior to 1 AU, in which case we'd all be living in water worlds or something like that. So there's a lot of uncertainty associated with this. I would say in the future, there are plans for missions that would actually locate the location of the snow line. And that would, I think, be extremely informative for protoplanetary disk models and, of course, for understanding how water delivery gets to the terrestrial planet, the habitable zone, and makes things actually habitable. So there's an enormous amount of uncertainty there, which is way beyond anything I understand. It's not my field, but yes, you're right. There's a lot of uncertainty there. Yeah.
This is a little bit outside your topic, but it's something that was. Oh, I'm sorry.
Yeah. Yeah.
Oh.
Hi. In one of your figures, I believe you showed a difference in model based on if it was a point source or a spatial object.
Yeah.
Does that mean it's possible to measure the planet radius in some cases?
No, it was the stellar radius, the source, the flashlight that we're looking at. Yeah. The planet radii are hopeless for this method. Yeah.
So we're running a bit late, and also I'll have an announcement afterwards. So let's just thank Scott again, and you can ask him questions later. And here is the special SETI mug
Oh, well, thank you.
that you always wanted.
Perfect.
And imagine it floating through space.